All right, so in this lecture I would like to talk about how you deal with the constraints on from a mathematical perspective, with the constraints that you get from hanging nodes and from other things like HP refinement, for example. So we talked about the meshes that you get when you do refinement, let's say local refinement of quadrilateral meshes. And the same thing, of course, happens when you do hexahedra. So I would like to give you an example where you use this mesh that we had at the end of the last lecture, which consisted only of 4 quadrilaterals, one of which had been refined, the top left one. And I would like to use the lowest order finite elements on quadrilaterals. That's a Q1 element. That is the bilinear element. So there's 1 degree of freedom per vertex. And between these vertices, we have a bilinear interpolation of our shape functions. So let me, for example, introduce an enumeration of these degrees of freedom. So I have 0, 1, 2, 3, 4, 5. I'm a C programmer, so I start at 0, 6, 7, 8, 9, 10, 11, 12, and 13 up here. So the total number of degrees of freedom that I appear to have is 14 here. That's the number of degrees of freedom in my mesh. So this enumeration, of course, is exactly what you saw in step 2, 3, and 4 when we call this function DOF handler dot distribute DOFs. Distribute DOFs essentially enumerates all the degrees of freedom in the mesh. And while the exact enumeration that the DOF handler class chooses is not exactly like the one that I chose here, the exact, let's say, which index to, or which number to put to which vertex, of course, does not matter that much. I just choose this as an example here. So if you look at this, then you can look at the shape functions that are associated with each one of these vertices, for example. And what you will find is that if I define my shape functions in the usual way, that means that, let's say, if I look at shape function 9 at phi 9, then I would say it is 1 at vertex 9 and 0 at all of the other vertices. Okay? And between these, I have a bilinear interpolation. So for 9, you know how this function looks. It's the typical hat function. But there's, of course, this pathology here at vertex number 1. So how do I want to define it? Well, so on these 2 cells here, I do as I always do. So I assume that the value of the shape function is 1 at vertex 1, and it is 0 here and here and here and here and here. But then on this cell here, I have to do something different, because 1 is not a vertex of this big cell down here. And in particular, if I want the value to be 0 here, and 0 here, and 0 here, and 0 here, and I want it to be a linear function on every edge of this cell, then the only possibility is that the shape function phi 1 is 0 on this cell, because it is 0 here, it is 0 here, and it's supposed to be a linear function on the edge from 0 to 2. That's an edge of this cell at the bottom left. So this function looks a little bit like this over here to the right. It is 0 at the bottom left cell. It is 1 at this one vertex. It decays linearly along these edges. And then, of course, it has a discontinuity along this edge from 0 to 1 to 2. And so this is a problem from a mathematical perspective, right? We want to have this, we want this function space to consist of continuous functions. After all, it needs to be a subspace of this function space H1. And so this is not a function that is continuous everywhere, and as a consequence, it is not a function that's in H1. So the problems that we face, if these are the shape functions that we choose, is it's not a subspace of H1, and in particular also if you think about, let's say, how we would assemble the bilinear form, or how we would define the bilinear form for our problem, which for the Laplace equation would be just the integral of grad phi, let's say grad UH times grad phi h with test functions phi h. This doesn't make any immediate sense because the gradient is not defined everywhere. Right? We have this place where the shape functions are discontinuous, and consequently the gradient of a discontinuous function would be something like a measure. Well, it turns out not just, I mean, you can always integrate a measure against a continuous function, but this is a measure, so it's something like a delta function along this edge, but this is also a delta function along this edge, and we don't know how to integrate a measure against a measure. So we will have to modify our approach a little bit, because clearly it does not work this way. So the solution that we have in these kind of cases is that in order to guarantee things like continuity, we need to require it somehow. So we need to add constraints to our space that require that the functions that we consider, so these functions UH and phi h here, are in fact continuous. So the way we do this is that we say, well, the space VH that we want to consider, that's our finite dimensional finite element space, we want to define it in the following way. So we want to consider the shape functions as always. So in particular, we would like this continuous function here to be a shape function. Okay. So these are the shape functions that make up this space, but then then of course all of the linear combinations of these shape functions are elements of this space as well. But we also want these functions to be globally continuous. So if I write the space as follows, so we want this space VH to be all of those functions little vh of x that are a linear combination of these shape functions phi I, but we also want them to be continuous. So this is an additional constraint that we pose to the space, and now the question is, how do we do this in practice? Right now I've just given you a verbal description of what we want, but how we want to do it in mathematical terms, that's of course still to be defined. So before we continue, I would like to really show you how these shape functions from which we want to make up the space VH, the ones that are not necessarily continuous, how they all look. And so I have a few over here to the right, but it turns out that I always find that it's incredibly difficult to visualize shape functions when they're static. So I prepared a file, a VTK file, where I have just output all of the shape functions into a VTK file, and then I'm going to use visit to visualize this. So this is the shape function, for example, that is associated with the bottom left vertex. It's the usual head function. You've seen it many times. And then I can go through all of these shape functions. The enumeration is slightly different than it was in the illustration that I had before. So this is the shape function that's associated with the center bottom vertex. Also, as always, here's, let's see which the next one is. Phi 3 would be the central one. Okay. Now the central one is an interesting case because it is defined on the three big cells. So the bottom left, the bottom right, and the top right cell. But then it's also defined, of course, on the little cell on the top left. And so you see the discontinuity here, right? And I can keep going down on this list. So this was phi 10, this is phi 11. Phi 11 looks like this. This is the one that is associated with the hanging node at the top right, or at the center right. So it also is discontinuous, and so on and so forth. So I can go through all of these shape functions, and you will find that some of them are continuous, some of them are discontinuous, and we have to deal with these discontinuities because they do not fit into our mathematical framework. Okay, so what do we do with this? Now, if you look at this problem, let's say from a purely algorithmic viewpoint or from an intuitive viewpoint, what you will find is that the only discontinuities that can happen in these shape functions are along these edges where there are hanging nodes. So these are the edges 0, 1, 2 and 2, 5, 8. That's the only places where discontinuities can happen. And you can also note that, well, so in this bottom cell here, for example, we always said that we want to have our shape functions be bilinear. That means, in particular, along every edge, that these shape functions are linear. So we want functions to be linear on this edge from 0 to 1 to 2. So along this entire edge, it must be a linear function. Now, if I want to have this to be a linear function, then the only way this can work is if the value of my solution, or the value of any function in the space VH that consists only of continuous functions, is if the value at this point 1 is exactly 1/2 of the value at vertex 0 and 1/2 of the vertex 2, right? So the value at the vertex 1 must be 1/2 of the sum of these two here. So I get a constraint that looks like this. V1 equals 1/2 V0 plus 1/2 V2. Only functions that satisfy this constraint and are linear combinations of all of the shape functions that I defined before are in fact continuous. And I can make the same argument over here on the edge 2, 5, 8, that only functions for which the value at vertex 5 equals 1/2 of the value at vertex 2 plus 1/2 of the value at vertex 8, only these functions that satisfy this constraint are in fact continuous. So this is a mathematical description of the constraint that I have stated here, namely that VH is continuous. So these constraints always have the following form. So there is a subset I of all of the degrees of freedom, which are hanging nodes that I need to constrain. Okay, so in this case on the right here, the subset I consists of vertices 1 and 5. And then for each one of these vertices, or for each one of these degrees of freedom in the set I must be able to express the value of the solution at this particular vertex as a linear combination of certain other ones. So I'm going to write it as a linear combination from j equals 1 through n DOF alpha ij vj. So it's a linear combination of the other ones. And of course, while I write this as a linear combination of all of the other degrees of freedom, in reality, actually, it's only very few other ones that it depends on. So for example, V1 only depends on V0 and V2. So the only entries in row 1 would be alpha 1, 0 and alpha 1, 2. All of the other ones are 0. Okay? So this is one way to describe it. Of course, I can phrase the constraints that I showed you on the previous slide. They exactly have this sort of form. Now, one of the things that I can do is I can bring all of these terms here over to the left side. And then what you will find is, of course, that this is a matrix times a vector equals 0. So I can write these constraints as some matrix C times my solution vector V equals 0. And the C is a matrix that has as many rows as there are constrained degrees of freedom, and it has as many columns as there are degrees of freedom in total. So typically, the number of rows in this matrix C is going to be fairly small, and the number of columns, of course, is equal to the number of degrees of freedom. But in every row, there are only going to be a very small number of non-zero entries. So it's a sparse matrix. We could store it as a sparse matrix, but it turns out that the way you typically build these sort of matrices does not quite fit into the same framework as you would build a sparse matrix, for example, for the linear system of a finite element method. So in practice, we store it with a completely different data storage format. Also, we almost never think of this matrix as really a matrix. So to me, in, let's say, a finite element context, a matrix is always something that I apply as an operator, right? So I ask the question, for example, well, if I apply the matrix to a vector, I get back another vector. So it's always a mapping, whereas this matrix C here, it doesn't really have that sort of, let's say, flavor. We don't use it in this way. And so in practice, when we build this matrix C, that's what we call the constraint matrix, we don't typically build this as a matrix, and we don't work with it as a matrix. There are many algorithms that we're going to use based on this thing that are very specialized to the interpretation of what this matrix is, namely hanging node constraints. So in deal.II, the class that represents this matrix C is called constraint matrix, and as I say, while it is a matrix, we don't store it as a matrix, and we don't work with it as if it was a matrix, but the name, of course, is still the same. It's a constraint matrix. And then the one function that you will typically have to deal with to create these sort of things is a function in a namespace called DOF tools, namely make hanging node constraints. And that's basically all you ever have to know. So you will never have to deal with hanging node constraints explicitly. As a user of deal.II, all of these sort of things are taken care of for you. You will call make hanging node constraints, and it creates a constraint matrix. And the constraint matrix will store all of the information that you need, but that's really all. There is nothing where you ever have to fiddle with the individual entries. You will not have to know how it's stored, and so on and so forth. These are the only two pieces of information you really need. Make hanging node constraints creates these things. Constraint matrix is the name of the class. I should also note that this constraint matrix is used in a number of other contexts as well. So in particular, you can do the same kind of argument, not just for H1 elements, but it also is true for things like, for example, Q2 elements, quadratic elements, or cubic elements. Or if you had, let's say, mixed elements where, let's say, you want to solve a Stokes equation. You would want to solve with Q2 elements for the velocities and with P1 elements for the pressure, for example. These sort of things. If there's a hanging node, the constraint matrix takes care of it, and the function make hanging node constraints builds this matrix. Then there's also a context that we will come back to in step 27, where we have HP refinement. HP refinement means that we have different polynomial degrees on different cells. So for example, we would have a Q2 element on one cell where the solution is smooth, but then we would have an H1 element, possibly refined, on a neighboring element where the solution is not smooth and where we cannot adequately represent it by a quadratic function. In cases like this, in the place where these two cells come together, you also have to enforce constraints, because you want the solution to be continuous. And so if from the left you have a Q1 element, the solution is linear, but from the right it is quadratic. And so in order for these two functions to be the same, the quadratic function must actually happen to be a linear function after all. So you get extra constraints also for the case of HP refinement. And so in practice, this constraint matrix is sort of a catch-all for all of these cases where you have constraints on degrees of freedom. And make hanging node constraints is the function that takes care of computing them. So how exactly it does this is not really all that important. That's the function that does it for you. So in order to work with this in practice, the next question, of course, is how do you actually use them? So I told you, let's say, where they come from and why we use them, but how do you apply them in the finite element context? And without going into much more detail, let's say one of the beautiful aspects of the finite element method, when you think about it, is that it's actually fairly simple, because you do exactly the same thing on every cell, right? If you think about how we assembled, for example, a linear system in step 4, we really just had a loop over all quadrature, a loop over all cells. And in there, we had a loop over all i's and j's, that's the local degrees of freedoms. And then we had a loop over all the quadrature points on this particular cell. We do the same thing on every cell. And what we would like to do, of course, is when we have hanging nodes, that we can continue to have this exact same structure. We do not want to destroy the property of this always the same loop. So in particular, what we do not want to do is when we assemble our linear system that we have to do something different for a cell that has, for example, a hanging node on the left, and something else different for a hanging node on the right, and then maybe something else different for a cell that has hanging nodes on opposite sides, and something yet else for a cell that has hanging nodes on adjacent sides. So we somehow want to keep doing the exact same thing over and over again. And so what I'm going to show you a little bit is just how the mechanics of this work. What I don't want to show you is how to let's say, the mathematical and algorithmical details of this work together. I wrote a paper with a colleague, Oliver Kaiser-Herold, in 2009 that explains this. I have to say that these are not things that we have invented, but there is not a whole lot of literature out there that actually shows how to do this in practice. And so we wrote it up in a very general context of HP finite element methods, but it also has a little bit of an overview of, well, so you have this linear system that you assembled as if there were no hanging nodes, and then there is this constraint matrix C. How do you get the linear system that you need to solve out of these two pieces of information? That's what you can find in this paper if you want to know the details. As I say, what I would like to show you is essentially the mechanics. So in order to do this, there is basically two approaches. And so let me introduce just a tiny bit of notation first. So I would like to introduce a space VH that is essentially just a linear, that consists of the functions that are linear combinations of these shape functions. So you've seen these shape functions on this mesh before. There were 14 of these shape functions. And so if I take linear combinations, because some of these shape functions are discontinuous, in general, these functions little vh are also discontinuous. And then, of course, we argued that we want to really work on the subset vh of this vh tilde that consists of functions that are linear combinations of these shape functions, but are also continuous. And we have argued that the way we can enforce the continuity is that we require that c times this vector of coefficients equals 0, where C is this constraint matrix. So I introduced these two sort of things because what I'm going to work with is essentially matrices that are built from this space without regard to constraints. And then, of course, if I wanted to solve the real problem, let's say if you wanted to write it in a mathematically concise way, I'm looking for a UH so that A of UH comma VH equals F comma VH. These UH and VH are functions that come from the space capital VH and not capital VH tilde, right? So we need to work ultimately on the matrix that comes out of this space and not out of this space. But on the other hand, because I argued that we do want to do the exact same thing on every cell, what we really want to work with in practice is this space here when we do our assembly. So the first approach to doing this would go like this. So in the first step, I built matrices in right-hand sets that I'm going to call A tilde and F tilde that I get from looping over all of the cells of my mesh and computing the local contributions and sticking them back into the global matrix in right-hand side. So I do this as if hanging nodes did not exist. Of course, these are the wrong matrices. So one of the things that I have to do is I need to modify these matrices A tilde and F tilde to enforce these sort of constraints here. And I get out of this a matrix A in the right-hand side F that actually do take into account the constraints. And this process I call condensation. So the class constraint matrix has a function condense that takes a matrix and takes a right-hand side, A tilde and F tilde, and modifies them in some way or other so that you get A and F out of this. And then I solve my linear system, AU equals F, and I get the solution U out of this. And ultimately what I have to do is I have to, well, out of this vector U here, I have to get back the vector of coefficients with respect to all shape functions, right? Even with respect to the discontinuous ones, because on every cell I want to be able to write my solution as a linear combination, for example, of the 4 adjacent shape functions. So I need to modify this coefficient vector here that I get out of the linear system again to transform it from the constraint space VH into the original space VH tilde that I always want to consider when I work on one cell. And this process is called distribute. So after solving, I have to, what we say, distribute the degrees of freedom from the constraint ones to the from the non-constraint ones to the constraint ones. This is the approach that I'm going to show you in the next lecture in step 6. There's an alternative approach that we use in step 22. Namely, we do the following. So we build these local contributions a tilde k and f tilde k, just like we did in the previous, in approach 1. So as if there were no hanging nodes. And then in approach 1, we would just copy or add these local contributions to the global matrix and modify the global matrix in a follow-up step. In this approach here, in approach number 2, what we're going to do is that instead, while we copy these elements from the local contributions into the global matrix, we're already going to do the modifications at the same time. So the constraint matrix has a function that is called copy local to global, and it takes a local matrix ak tilde and a global matrix A, and it copies these local contributions into the global matrix, and at the same time takes care of the constraints CV equals 0. And it has another function copy local to global that does the same thing for the right hand side. So the global objects are immediately the correct ones. I can solve the equation like I always do, and then I can call distribute to get the coefficients or the components of u in the space v tilde that I want to work with. I think that one can make a reasonable argument that either of these two approaches work just fine. One of the things that you will find eventually is that the approach number 2 is slightly more complicated than approach number 1, but it has a number of advantages. Namely, the primary advantage is that once we have built a sparse matrix capital A, or a vector F, we don't typically want to touch it again, because it's expensive to muck around in the sparsity pattern of a sparse matrix. And it is damn expensive, maybe even impossible to do these sort of operations on matrices if they are distributed on a parallel computer. So when we do parallel computations, we don't have this matrix A on every computer. We only have individual pieces of it. We have, let's say, a number of rows that we store locally. But so this condensation operation that we have to do to get from A tilde to A requires us to have access to all of these elements of this matrix. And so the approach to condense the linear system after it has been built, or after we have built the wrong one, isn't going to scale very well for the parallel case. And so for these sort of situations, approach number 2 is far better. There is one last point where approach 2 is worthwhile, namely when you have a very large number of constraints, and that's what happens typically in the HP finite element method, where you have, for example, 1/3 of the number of degrees of freedom are actually constrained. In that case, approach number 2 is better suited. I'll show this to you in step 22 when we come back to this. So, having introduced these two approaches, the next lecture will be on how to use this in practice. So I'm going to show you how we use this in step 6, where we actually solved for the first time on an adaptively refined mesh.